This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Thank you. I'll make a start. Thanks especially for coming and being here at 9 a.m. on a Tuesday morning. Material selection in a systematic way. That's what the first topic in this subject is, and I'll provide an introductory lecture right now. I won't finish this lecture one today. That's 70 odd slides, but we'll make a start. Later on today there are 3 repeats of how to use CES, Cambridge Engineering Selector, plus there'll be plenty of people in the room, plenty of demonstrators in the room. I've allocated 4 people because I get it. Keen students want to get started quickly onto an assignment, so please make use of that resource. Lecture 3 is the one down the bottom, which it's just essentially a how to use it. CES is not a difficult package. It's essentially a very, very big database with an overlay of how to interrogate that database in intelligent, dare I say, systematic ways so that you, the engineer, can draw on candidate materials for the task at hand. Now, that word systematic is important. This topic is all about an approach to material selection that is systematic. It enables you to look widely, dare I say creatively, divergent phase of the design process into the universe of materials, and then to come down and narrow your search with respect to your objectives and criteria. So, material selection today, and then I'll get onto shape-based issues and how that impacts on your candidate material selection process and which materials might become optimal that weren't optimal when you weren't considering shape, and I'll tie off with a few case studies. And a lot of this material comes from Professor Ashby from Cambridge University, still alive, still publishing, which is very nice to know. You can get an online version of this book via the library, download it, have a look at it until the PDF expires. So for those who want to go a bit deeper, you're more than welcome. The one thing I'll say though is this is not meant to be hard. This is meant to get you, into the academic year, into this subject in a smooth and easy way. So please don't overthink it. Don't think that there's more to have to understand than what there is, because I hope to get to the key slides today, and if I don't, well, I'll just point them out to you for next time. Okay, some hand-waving fun and games. What you're seeing an image on now is, as of 2013, it was the world's longest and largest wind turbine blade. Not anymore, but the key point I wanted to make here is that it's one great big mould. You can see it there in an image when it's been made, but there's a chap there in the foreground working up the mould into which all the materials will go. Made by Siemens, made out of fiberglass, 75 metres long. Now, this idea of having one long piece, you've got to find a pretty big warehouse. You've got to make sure it's perfect all the way through because you can't have any flaws. But there are advantages. To create it in one go rather than a series of smaller elements and then you somehow glue or attach or bolt, weld, whatever attachment process we have them together, Siemens claims a 10 to 20% lighter blade. Now that's a big advantage. That's the sort of thing that the creative engineer will say, hey, accountant boss, we need to build a great big temperature controlled, climate controlled, factory, where we can make one of these in one go. And I want us to do it because of savings such as this. And then the accountant might say, well, what does that translate to in terms of cost effectiveness or efficiency in production or efficiency in use? Well, that's the next stage. And that's not hard for an engineer to be able to calculate. Current technology, our emerging technology, there is an advantage. Are we prepared to take that risk? You know, Siemens was and did. And there's a whole YouTube video that you can have a look at where they go into it with a bit of marketing as well. But it's no longer the longest. As of 2014, I got this via Google. There's a wind turbine, and I just looked up world's longest wind turbine blade. There might be something more longer than that now, because after all, 2014 is a few years ago. We've got a blade length of 82 metres, so another 7 metres on top of what you're seeing now. But nonetheless, I talked about factory. How do we make something that's that long in one go? Differential cooling, are we going to get cracks? Do we have to think about that? Of course we do. All the material science stuff that you've hopefully learnt a bit of already. But then it's critically important, and John Weir will be talking to you about this in the context of pressure vessels. There are other issues for the designer to think about, and what's on the screen now is one of them. You've got this great big, as light as possible, you know, flexible as possible, you know, flexible in a way that will optimise its engagement with the wind when in service. But still, this component has to be transported to site where it will be installed and, you know, start producing electricity. So these images are just communicating some of the issues that the engineers had to deal with. The installation process in itself is probably a very expensive customised device there to hold the tip end of the blade. The installation process, very high crane, etc., etc. Yeah, it's no longer an emerging task. It's in terms of difficulty, an issue. The engineering has already been done. The trials and the mistakes, by and large, have been made. I know nothing about ocean-based or, you know, very calm ocean-based turbines, but I could imagine there was a whole heap of issues there when you'd have various floating devices having to transport these components out and then lift them up and to bolt them together. You know, that's the nacelle where the gearbox and generator reside, and the rotating component has to attach onto the drive shaft. The precision of doing that when you're floating on water, I am very confident would create a whole distinct set of engineering problems. If you're ever lucky enough to be in that situation, learn and tell me, please. I'd love to know. Give you an idea of perspective or proportion. And as I've said, this is no longer the biggest wind turbine on water in the world. That's a Airbus A380, and you know, I've seen one of those up close. They're fantastic and big. And just think how much projected area that wind turbine is capturing in terms of wind coming in compared to the size of an A380. They're big things. But you, the engineer, are learning not just to be impressed, but to dive in. You know, what is it about a turbine blade that makes it interesting? Now, up on the screen now, I'm not going to go through all the blah, 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 but this screen is to just say there is a lot of stuff associated with a turbine blade. There is a lot of engineering therein. And one area I know is still emerging, which is, you know, it isn't finished, is maintenance. You know, how do we check that a turbine blade that's 154 metres up, oh sorry, not that way, you know, whatever, up, plus another up, and you've got to somehow be able to detect if there's a crack or not. Can you do some maintenance on that crack if you can actually detect it? Now, I do know some colleagues in Germany that are playing around with drone-based technologies, essentially a series of drones holding a cradle. Of course, the turbine stopped operating, and that cradle has essentially got a hole in the middle and goes up through, let's say it encompasses or goes around the blade, and it's got various sensors that looks for, X-ray machines, infrared cameras, that looks for imperfections in the blade. But as of now, there is no one technology that's won that battle. And I know in Australia, what people just tend to do is, from ground level, just look up with whatever technology they can get. And local drone manufacturers are playing around with the same set of ideas. Something emerging, something you can think about. This is a slide that's given you an idea why carbon fibre, glass fibre, all this kind of, these composite materials are winning the race at the moment in terms of choice. Why, I've talked about carbon fibre first thing. Why isn't that a steel or aluminium blade in toto? Well, here's part of the reason why. Aircraft, wind turbines, etc., they want high strength, low mass. They also want to be reasonably high stiffness with low mass. The overall word is specific in that regard. Young's modulus or stiffness modulus with respect to mass is what we call the specific modulus. Strength divided by mass corresponds to the specific strength. And up on the screen now, and I don't expect you to read it from the classroom, but let me promise you, titanium, steel, aluminium in that zone, glass epoxy composites up there, and look, they're right near the zero. We go over here where we've got graphite epoxy composite, boron epoxy composite, something called aramid epoxy composite, and they're way, the numbers are far higher in terms of specific strength and specific stiffness. Not surprising that people are prepared to spend the money to have that very first slide, to have the factory, to make the carbon fibre turbine blade when there's this kind of advantage just from a screenshot like this. Same type of information, different form for those people who like bar charts. Specific strength and specific modulus of metals, that's where they are, and composites, that's where they are. And you can just see the bars are an awful lot higher. Here's another one, bit of fun. This is called the Sail rockets made by Vestas. There's a website you can go and have a look at for more details. The bits down, the little bit of like stop animation video down the bottom is just giving an indication. These things don't ever work first time. Any evolving, any new technology, you're going to have a few breakages along the way. Thus, I talk a lot about safety. You guys, Warman, hopefully everyone in the room, or most people in the room have done the Warman design build. Second semester design for integration, there will be a model made of your industrial gearbox for various reasons. But the making of it, the realising of an idea is part of my intent. There's a couple more photos. It had an extraordinary aerodynamic advantage. And again, it's not made out of steel. That orange fuselage is made from a carbon fibre composite. You can imagine the whole device, high strength, high specific strength, high specific stiffness, and those two notions are being stated up front on purpose because they're coming up in a more part of the systematic design approach in a little while. Now, from the sublime to the more mundane, that image is to remind me, I don't know if any of you have ever seen me riding my bike around the place, but I do ride to work every day. And a few years ago, I got knocked off my bike, and I was all right, in case you're wondering. But survived the crash, but my poor old front fork did not. When I first bought this bike, it was sold to me. I might leave the video on for one, so you can just, as I start wobbling it about, at least you can. Come on. Everything else about every other part of the frame was aluminium. I was sold on the idea that the front fork was carbon fibre, which had a not stiffness and strength, but it had a nice dampening property, that you hit a pothole and you don't get that shock going all the way through to your hands and arms. Anyway, A lot of them are like that. But with the advantage comes some problems. And this is just beyond me falling off. You can see that pretty, carbon fibre type crisscross going on there. But the reality is a lot less fancy. I'm just trying to get the shadowing because it's hard with black. On the inside, there is no fancy weave. It's as if it's all just been slopped in there. And this edge is something else you can pick up on. It's not even as if it's a consistent thickness. The outside edge has all been nicely polished, but that's essentially a thick paint. Second issue is carbon fibre is great for certain things, glass fibre the same, but it doesn't have, let's call it Hertzian strength or contact strength. When we get to a point where we want to have a lot of stress going through the object going through a small area or a small contact zone, we've got to have some way of interfacing our carbon fibre because it doesn't have advantage anymore to a bit of, here we've got aluminium. Make sure I get it right. Investment casting is what we're talking about. So we've got, at either end there's a casting. We have to have tolerancing to be able to allow for the carbon fibre strut to slot in. There's got to be a big enough gap to allow a bit of glue. That's how this thing's been attached. And then we ask, how precise does it need to be for a push bike? And the answer, of course, is we're looking at price point. We're looking at cost. It's not aerospace. So you could imagine it's not going to be as fancy. And the same thing is happening down at this end. And this is where the axle for the front wheel would go. And I don't know how many of you know Octay down the workshop, but he kindly chopped this up for me. Again, I apologise for the black and the bad lighting, but you get a bit of an idea that there's the carbon fibre, there's the aluminium insert, there's enough gap there for glue, and you might also note that this was a good thing, that someone, let's just presuppose it's an engineer, decided it'd be a good idea for a bikes are meant to be lightweight, to cut out, to have a blind hole, to cut out at the centre so that there's less aluminium to have to be carting around as we ride our bike around the town. So, one more thing. I was all right. Every bit of aluminium on the bike was all right, but only when, and even when the bike mechanic had a look at it, he didn't notice. Only when I did. Hopefully, everyone in the room can see me playing around with the other end of the forks. Oh, there we go. You can see the crack there. You can also hear that I just gave it a pop somewhere along there, which wasn't the intent of this presentation. But once that's happened, it's finished. And for those people who've got fancy whole frame carbon fibre bikes, thinking, oh, yeah, that'll be great, that'll last me a long time, don't be so confident. First crack is the end of the frame. You can't. We're not talking about yield strength going to ultimate tensile strength, and you've got a long elastoplastic zone, as with steel. Once this has happened, we can't trust it anymore. This could just pop off at any time, just like that little cracking sound you heard just then. It's got to be replaced. So that's a downside. Now I've given you that little blurb in part to get so that everyone in the room doesn't have stars in their eyes that the future is carbon fibre or glass fibre or graphite fibre. It has to have. It'll have its place, and it does have its place, but it also has its disadvantages. And that's just something to take out of this lecture. Things can go wrong. This is another example. It's a bit more mundane. Steering knuckles for automotive applications. Again, even in cars, people are looking for lighter weight. and anything that's it's beyond the tyres and spring damper system, the unsprung masses of the car. People are going crazy trying to cut back on how much that stuff weighs. One example, and this is a guy called Martin Leary, now a professor down at RMIT in the Advanced Materials Centre. This was a little bit about his PhD that I supervised him for. We had a local company that wanted to convince Holden at the time that they should move from steel knuckles for their drive chain to aluminium. And so we've got a forged steel casting of 4 kilos, and that's one of Martin's prototypes. And we almost got to that point. We almost halved the mass. We had to use, all the available tools at the time. So finite element analysis was used to try and shave away as much material as we could where there was no stress or minimal stress in that material. And that's, shape optimization is a big deal now. It was quite new when we were working on this. So obviously, where it's red, there's an awful lot of stress. So add material where there's a lot of stress, take away material where there's no stress. We still had to accommodate all the holes and all the connecting points to the other existing components, and we had to work out what the stresses associated with that would be. We also had to think about the existing testing regime. Automotive manufacture, it's not as tightly controlled as aerospace, but it's still pretty tightly controlled. We had to have 10 to the 8 cycles, so 10 to the power 8 cycles, and still not have any evidence of cracks. And every so often, we had to take it off the fatigue tester and put it onto other testing devices that would simulate, say, a wheel bumping roughly into a curb or going through a pretty deep pothole. So we had to, that was the process. And so we got a successful outcome. So it's not all about, carbon glass fibre. You can have material replacement with something as simple as steel to aluminium, or if you like, steel to magnesium. And Peter McGowan will talk a little bit about that in a practical sense, the reality of a man who's spent a lot of time doing these sorts of things in a week or two. Here's another fun little slide. The idea is, this is like 10,000 BC and about now. Ceramics, composites, polymers, metals, and the rise of metals as the dominant in around the 1940s, 1950s, last century. And this line going up isn't saying that metals are becoming more prominent. It's saying that their relative scope compared to polymers, compared to composites, compared to ceramics is actually diminishing. Steels had their, metals had their peak, a few generations ago and are reducing in importance, whereas polymers, elastomers, composites are somewhat growing. It's also interesting, you might think, that ceramics had a big, it's up there, stone, flint, pottery, glass, cement, and that dropped off a bit. But now with glass fibres and ceramic fibres and exotic type materials, they're growing in popularity again. This is just something as a trend for you to think about. If you like, engineering. They might not have called it engineering way back then, but it was the same kind of thing. How are we going to make our hut? How are we going to make our house? How are we going to make our aqueduct? Whatever it might be. And we move on to some of the more, it's like the pinnacle of whatever, pushing the edge of technology. Again, I've got no input I've not got any inside knowledge of what these things are made of, but we can be pretty confident they're made of materials that are quite exotic indeed. And in fact, this F117, there is quite a bit of information on the web now about just the nasty stuff they used to coat that fuselage with to give it its, that radar invisibility notion that they kept pushing. And there's quite exotic material science associated with it. And of course, they use the the ideas that are generated, what is new and revolutionary, evolves into things like the Raptor or the F-35 Nighthawk that Australia's just taken delivery of two thus far. Commercial airliners, 787, carbon fibre fuselage. The fun part about this plane is how the hell do you lay out the fibre on a very long, with discontinuities, where the wings go on, how do you connect the wings to a carbon fibre fuselage, make sure the engines don't fall off. There's a whole heap of technical issues that the engineers had to deal with. And after launch, there was still a little bit of, let's call it beta testing issue. You might remember, this is a few years ago now, 2013, there was an issue with lithium-ion batteries catching on fire. And it was an issue for about a day. You know, of course, the media makes a huge deal out of a bit of smoke coming out of the fuselage where these things caught fire. And then it just disappeared again. You know, Boeing took them out of the air for a little while. It turns out that lithium-ion batteries need a better airflow than the old lead-acid batteries that they replaced. And it was just, let's call it an omission, an oversight by the engineers that they didn't have enough airflow to keep the greater amount of heat that was being produced being evacuated from the zone. Temperature got too high, the battery caught fire, you know, problem at the time, no risk to anyone, but the problem was solved, which is one of the great things about being an engineer. You think, okay, problem today, address the problem, solve the problem, no more problems. No one talks about it anymore. And I haven't put it on these slides, but I have an assertion that the public only cares about what we do when something goes wrong, because that's when the media jumps on board. And to be blunt, it's part of our job to make sure we don't get into the media. That the magic that is technology just continues to work for society. And it has. In this little funny example where, I don't know how many people care about these old wooden, brass type phones, but it's what people used to use. They were the height of technology at one point. And now, you've got to think, these slides aren't that old, but 2018, you could say, okay, we've got to have another series of iPhones there, and there's, I forget which brand it is, sorry, but there's this fold-out phone now with a hinge that, I haven't seen one, but I'd love to know how, what the continuity of the screen is when you've got it folded out. But, and there's some fantastic technology there, but as a phone, what else has that one got going on? As an underlying technology, there's probably some extraordinary bits of IP that someone or some lab or some engineer is making a lot of money out of. But the overall process, the overall evolution is interesting, and the materials of choice are interesting. Now, the first iPhone had a very nice sculpted aluminium back and high tensile glass. And it's probably the same kind of glass, aluminosilicate glass, so they try for high scratch resistance. It's got to be jam-packed full of all those little wires to allow for the touch sensitivity. But there is a consequence to having that kind of glass on the phone. I don't know how many of you have ever dropped your phone, but they shatter. And costs quite a bit of money to get that glass replaced. Now, just with this one, the 4 versus the 5, and they have fixed this problem, I regard it, as being, when this one came out, you can't see it on the screen that well, but just look up iPhone 4. And when I first saw one and touched one, I thought, my God, that glass is it's proud, or in other words, projecting beyond the aluminium side. And there was this sharp edge of glass going all the way around. And I thought, gee, I regarded that as a design fault. Dropping the phone in just the wrong way would result in the glass clipping the ground first, and that impact load would be enough to cause the shattering. It wasn't long before Apple put, I'm sure it's a polymer of some form, around the edge, just like a bumper bar, a safety bumper. So that bit of rubbery plastic absorbs some of the impact load before the glass comes into contact. So, materials. few examples. Up on the screen now is just a mud map or concept map of the world of materials. Metals, ceramics and glasses, foams, natural materials, fibre, wool, hemp, cotton, wood, polymers and elastomers. And to be blunt, a composite can be, any combination of those things. A composite doesn't have to just be, some kind of polymer with carbon fibres or glass fibres. You can have a composite of steel and aluminium powder if you want. And with the rise of 3D printing and metal 3D printing, I predict that that'll become more of a thing into the future. Now, as you think more about this stuff, will have to think about material properties and also material processing. That is, it has to, the design that you want to achieve has to have a certain performance against the specification to which you're working, but then it has to be makeable. It has to be it must be able to be realised, and that's one of the in this course here at Melbourne, I would argue you don't perhaps get an awful lot of this. Now, of course, that's not. I'm telling you this just so you know what the deficit might be, because you get a job and you start thinking, okay, yeah, done a few design subjects, I'm really good at math and science, time to start making some decisions and going forward. Don't forget, it's got to be able to be made. And if you don't have the skill set or don't have the experience, you do the research yourself, or you get someone in. You employ a consultant, or if you're a manager, employ an engineer that has done some of this stuff. In that way, the team, all moving towards the same goal, is better able to achieve that goal without iteration. You don't want to have to iterate more than you have to. Here's a little bit more. We're moving towards that systematic stuff now. The world of materials, the family of materials. So instead of having that little mud map, now they're just listed. We've got classes of materials within each family. We've got members of the class within each material. And then we've got a set of attributes associated with every specific material that theoretically we'd be able to buy in the right kind of shop. Now, I say theoretically because when you start playing around with CES, you'll think, oh, there's so many materials. But actually getting your hands on some of them might be very, very difficult or very expensive. Now, the attributes, and part of that, another word we might use is engineering properties or mechanical properties. That's the specific stuff to us, but the idea of attributes can perhaps extend beyond what we care about for the problem at hand. And up on the screen there is a heap of stuff: density, mechanical properties, thermal properties, electrical properties, optical properties, corrosion properties, supporting information, which in CES can even include potential sources where you can buy the stuff. And all those attributes can be regarded as a material record. Now, when you get to that point, that's the starting point for design, the kind of design that you are used to. We've got some engineering science principles. We've got some structural integrity issues. In which ways might our device break? And we've got to get some numbers to be able to put in there to find the limits of performance. Now, again, lots of very small words which I don't expect you to read in the classroom, but just the idea of what we've got going on. We've got data from tests. We've got information associated with those tests. And you, the engineer, will think about incorporating that information into useful applications so that then people want to buy it, whoever that might be. Companies, the general public, whoever. It doesn't matter. That's the overall process. And for you to have an awareness of all this stuff, at least by the time you graduate, will be something that employers and the average member of the public will expect of you. Of course, weight, easy. Expense, everyone gets that. But when we start moving into stiffness strength, fracture strength, tensile strength, brittleness, etc. We're moving into technical, specific knowledge now that the average person would not be able to nominate intelligently, but you can. Thermal and electrical, again, issues that let's say electrical, you're not doing an electrical engineering degree, but there'd be an expectation that you'd have a basic understanding of electrical performance. So, for example, you're designing something, and look, with the rise of electric motor-based and computer control-based technologies, let's call it mechatronics, the idea of thermal conductivity versus electrical conductivity, by way of example, would be, again, something that every mechanical engineer should be aware of, at least aware that we've got to investigate both because they're different. So, just a couple of examples. A couple of aeroplanes, aircraft wing flexibility. How flexible does an aircraft wing need to be? Now, up on the screen now, a few things: stiff, strong, tough. Tough implying a bird strike. A bird hits the wing. Is the wing going to disintegrate, or is the wing going to get a dent in it and it has to go into maintenance and it'll be okay, no one dies? Light, that is, we don't want to use any more jet fuel than we absolutely have to get that aeroplane and all the passengers from one place to another. But if it's not stiff enough, it'll wobble too much, flex too much, and that's all about Young's modulus. Young's modulus too low. Not strong enough, it breaks, bends. We need a higher yield strength. Not tough enough, it fractures. We need a higher fracture toughness, K1C. Now, fracture toughness is something I teach in Design for Integration, so don't worry about it now. Just since I've brought it up a couple of times, I don't know how many of you people eat bags of chips or bags of lollies, those plastic bags that, if you pinch and tear across the serration, it's very easy to create a crack that propagates. If, however, with that same material, try and do a tensile test. Now, everyone's done that, I hope, with an Instron machine. Grab either end and try and pull it apart where there is no discontinuity and see how high if you like, the ultimate tensile strength is going to be. Ultimate tensile strength versus fracture or crack propagation toughness, they're two totally different engineering properties. And again, bag of chips or bag of lollies made out of plastic, you get an idea just how easy it is to break the bag or open the bag one way, how difficult it would be the other way. So fracture toughness versus strength. And lastly, too heavy, the weight's too great, density's too high, the wings are sagging, really bad. Property profile. Not just the engineering, but we'll get onto that. We've got constraints and objectives in the language of right here, right now. Constraints are non-negotiable or hard. They can also be desirable. That turns into a restriction in the context of mechanical design, the first subject in this series. And a constraint must be, say, it floats on water, whatever it is. It's going to be a boat, or it's going to be a life vest. It sort of floats on water is not good enough. Or it must fit inside a specified volume, like the steering knuckle I talked about earlier with Martin's PhD. I said how that had to fit in the existing available volume of the car and had to hook into all the existing components of the car. And objectives, by comparison, define performance: minimum mass, minimum cost, maximum safety, etc., etc. And for the systematic approach, we've got to do both. Now here's a few more. We're hardening the information in an initial appreciation style now. The constraints. Float on water, well, we turn that into some numbers. So density, if it's just an object, density must be less than the density of water if it's going to float. Or the effective density, you've got a shell with a volume inside the middle of it, like a ship, steel hull, lots of air inside, it still floats. Spatial constraints, it can be just a metre cubed, or it can be a x metre by y metre by z metre, or even more complicated, depending on the shape we're looking for. And then we've got to have a ranking or a rating. How important are each of those two, for example, constraints? And again, the objectives: mass, cost, safety, kilograms, dollars, pounds, whatever. Maximum safety, I've got their subjective rating, and it can be. Maximum safety, of course, if we're going to be absolutely safe, we'd never get anything done. To live is to live in risk. But the deal with safety, and people like Stephen Beard, who is our OH&S, Occupational Health and Safety Officer here in our School of Engineering, he bangs on all the time about safety. And he understands that we've got to do stuff. We can't just wrap ourselves in cotton wool and just lie in bed all day. So we've got to have, there are systems that Stephen has, and again, when you get to final year capstone project, you'll engage with that a bit more deeply. Subjective ratings of how to be safe enough. What is safe enough, and what do people regard as how much money are we prepared to spend to be safe enough? Aerospace, huge amounts of money is spent to be safe enough. In this lecture room we're in right now, you can imagine it's an awful lot less. In that notion, 10 out of 10 for an aeroplane, safety might be 2, 3 out of 10, 4 out of 10 in some of the designs we're thinking about here, because consequences aren't terribly dramatic. That whiteboard, those whiteboards don't work for me. It's irritating, but no one dies. Compare though, if one of those projectors falls out of the roof and hits someone on the head, I'd change my mind and say from 4, I'd pull it back up to 10 again. We'd have to have that, someone do the bolting of it, someone else come along and check it, someone else give it a wobble, and then periodically someone come along to check that it's still safe. Does the university do that? I bet it does. I bet it doesn't. But safety-wise, for you, who's just sitting right under it, I bet you'd love to know that the university has a crane come in every year and check the bolts to make sure it's still sitting there. I would. That's why I never sit under them. I'm a nerd. I do think about these things all the time. Here we go. Got a few more minutes. So, we're moving towards a series of charts, and that's the Ashby type charts. And this idea of constraints filter acceptable materials, and objectives assist in ranking the acceptable materials. Everything else on that slide is just moving towards the same data. Property limits and material indices are what constraints and objectives provide us with, respectively. So, we've got these design requirements. Function, what does it do? Constraints, what is the... Now, plural constraints, but we have to always think, well, what's the most important thing we're working on right now? And this is one of those simplifications that you just have to live with for now. You try and make this stuff more complicated, and the systematic approach sort of breaks down a bit. It's not like a computer program that'll give you the answer. It gives you guidance towards the answer, and it will reduce the candidate material population down to a manageable number. Instead of thousands, you might get 8, 10, 5, which is something manageable in our finite minds. Objectives and what variables are free and not really relevant to the problem at hand. And then we can do a screening of go, no-go criteria, what's important, and we can do some ranking. Which materials are actually important? Let's start with heat. Why not? Heat sink. We've got our fan, we've got our circuit board, microprocessor. Now, this is a snapshot of that very process. We eliminate the materials that can't do the job, and then we find materials that does the job best. So constraints must, for example, operate at 200 degrees, conduct heat well, but at the same time be an electrical insulator. So then we will retain or consider materials with a maximum surface temperature. We're going from Celsius to Kelvin, a thermal conductivity value, and high ohms, whatever, and high ohms, electrical engineer would say, oh, it must be greater than 100 ohms or 10,000 ohms. that would be one of those numbers, another number that would have to be given. And then an objective of minimum cost, well then we rank the materials by price per kilogram or by manufactured price per kilogram. An ingot, just raw material out of a factory, versus something that has to be manufactured, 2 different price points. Now, in this subject, I want you to be aware of it, but you do not have to do any detailed work on it, because it's not fair. If you're a practicing engineer, and all companies, all they ever talk about is money. So the price to make, the price to buy, there'll be teams of people to spend hours and hours working on that. It's not as if you have to just pretend. It's enough to think about the contributions for now. As I just said, the raw material price versus the manufactured price, plus perhaps transportation price, plus perhaps issues associated with manufacture if it's got consequences, like it has to be in a specialised environment, requires specialised equipment. All issues for the engineer to have to think about. Now, this, number 1, big circle, this is the, if you like, start point of important examinable part of your assignment, DP1 material. We've got, and it's also a template that's going to be repeated for those who haven't read ahead. Function, objective, constraints, free variables. And we've got this idea of strong, light, tie rod. Strong implies strength and stress. Light is that word specific, or divide by mass. Tie rod implies the graphic you see. That is something long and thin with axial tensile force on the ends of a certain cross-sectional area and a certain length. And if our objective is to, light implies minimise mass, well, there's an equation for mass. If the length is L is specified, must not fail under a load F. And I could also say, must have adequate fracture toughness, although, as I've said, that we can only do one thing at a time, and that's why that's in orange. Fracture toughness might be a secondary filter after we've got our first set of candidate materials based on this equation for A, which gets us down to this particular equation for mass. And we want to try and minimise mass. We've got a force that's constant, we've got a length that's constant, so we're choosing materials with a smallest, we're looking at less than or equal to type stuff now, inequalities, not specific, equations with one answer. Materials with the smallest ratio, density to yield strength. If we wanted a stiff, light tie rod, everything else is very similar, except now we've got this idea of Young's modulus or stiffness modulus E introduced into the mix, and the variable stiffness is actually incorporated there. Now, I've put that up there for a purpose. There it is. Stiffness, force divided by associated deflection at that force. And deflection is one of those values that we pretty much look it up in the back of the textbook. Or you guys look it up on Google to get your equation. In my world, that's why I put all this sort of stuff. It's a busy slide. That's top right-hand corner. I'm putting it there, and it's my promise to you that I will not ask you to memorise stuff. And if I ever do, I'll say it explicitly. The back of the exam, when we get to the exam, it's going to have a wadding great big page after page of equations and tables and look up stuff. I won't be directing you to where to go, but you just have to say, okay, Colin doesn't require us to memorise, it'll be there somewhere. There's the equation I need. That's the skill I want from you, to be able to get the information you need when you need it. And beyond all that, and I'll stop in a sec, we're looking at proportions. Stiffness is proportional to area. Stiffness is proportional to Young's modulus. Length is constant. So we can rearrange our equations into mass being the dependent variable. And I've got there proportional to, yes, that is not not an alpha, it's proportional to. S and L naught, if L naught is a constant, L naught squared is a constant. So as far as I'm concerned, we can just cut those two things out for stiffness and length. And now we've got choose materials with the smallest density divided by Young's modulus. So density divided by yield strength, density divided by Young's modulus. We've got to a nice point. The very first thing I talked about, stiffness relative to strength and stiffness relative to stiffness. And we've got, after all that time, we've got this simple little inequality that we can play around with. The same process occurs for beams, stiff light beam, same essential process, cut out all the constants, and we get to density divided by Young's modulus to the power of a half, which is a little bit more interesting. For a stiff light panel that is flat, thin, all the same mathematical process, and we get smallest density, rho, divided by Young's modulus, E to the power of 1 on 3, which is rather interesting. So right now, and I'm going to stop at this point, we're building up towards having some equations that we can use for the systematic approach that I've talked about. I'll stop now because it is time to go. Don't forget tutorials today to get you into Cambridge Engineering Selector, and design workshops are occurring this week for your DP1. I'll see you later.